Good afternoon, everyone. Good afternoon. Hope all is well and everything is all right. Um, like a few people still trying to connect, but hope everything's good. Hope everybody's ready to get this, get out of this week, get ready for the weekend. Um, let's see. We left off what section? I think we're supposed to be getting into 5-1 today. Anybody have any questions on anything before we go into a new section? Everybody good? Everybody straight? All right. Okay, no questions. All right, so I believe we covered 4-3 last class. Yep. Talk about not assignments. All right, so just making sure we're good. All right, so let's look at 5.1. So 5.1 or chapter 5 starts with probability. And probability is going to be the measure of the likelihood of a random phenomenon or chance behavior occurring. All right, next thing he mentioned is the law of large numbers. And that just says as the number of repetitions of probability experiment increases, in other words, the more you, let's say if we're talking about flipping a coin, the more you flip a coin, the proportion with which a certain outcome is observed gets closer to the probability of outcome. So the more you perform an experiment, the more you get closer to the actual probability of that experiment. So the law of large numbers. As always, if I scroll up too early, let me know so I can scroll back down. All right, so experiment. It's going to be any process with an uncertain or with uncertain results that can be repeated. So example of that, as I mentioned before, is flipping a coin. All right. So the sample space of an experiment is the collection of all possible outcomes. Normally it's denoted by S. In other words, we call your sample space S. An example of the sample space of flipping a coin would be heads and tails. There are all of your possible outcomes, heads and tails. All right, an event is any collection of outcomes from the sample space. So Tails could be your event. In other words, if you ask the question, what's the probability of landing tails? Tails would be your event. And then that's normally denoted by any capital letter. Normally you wouldn't use S because remember S is going to represent our sample space. So we can call it T for tails. Everybody good so far. All right, two rules of probabilities. Yeah. Yep, that's not how you spell probabilities. All right. So, first one, the probability of your event is in between, or it will be in between 0 and 1, inclusive. So it is possible for it to be a 0% chance, or 1 would be a 100% chance. Those are possibilities, but normally it will be between 0 and 1. When you see P parentheses E, that means P of E. That's how you would say that. And then probability rule 2 is that the sum of all of the probabilities in your, the sum of probabilities of all of your outcomes will be equal to 1. So when you add up the probabilities of each one of your events, each one of your individual events, they will add up to 1. All right. All right, so the probability model must satisfy rules 1 and 2. So they give you a model and ask you to verify whether it's a probability model, you have to check it against, once again, those two rules, rules 1 and 2. Do each one of the probabilities add up to give you 1? And is each one of your probabilities in between 0 and 1? All right, gotta let me know how much a little is. I don't know if that's good enough or not. All right. So we're looking at this chart. We want to see if it is a probability model. I'll scroll all the way up in a second. But we have colors of choice: brown, yellow, red, blue, orange, and green down there. Like I said, I'll scroll up in a minute. And then on the right, we have the probabilities: 0.13, 0.14, 0.13, 0.24, 0.20, and so on. You know that 0.13 converted to a percentage would be 13%. Then it'll be 14%, 13%, 24%, 20%, and so on. All right, can I scroll up a little? Are we good? All right. So that's the rest of the chart right there. We have green as our last row, last category with a 16% chance. All right, so to verify the probability model, first rule is each probability between 0 and 1. Hold on, guys. Sorry about that, had to sneeze. So rule 1 is each probability between 0 and 1. Checking these, the answer is yes. So each probability is between 0 and 1. Rule 2, when you add up your probabilities, what do you get? So we see adding up our probabilities, we get 1. And since the model satisfies both rules, it is a probability model.
Quick question.
Mm-hmm.
So what if we have a situation where the thing doesn't add up to 1? Like let's say the addition ends up being 0.96. Is that still good, or it has to add up to 1?
Well, yeah, it has to add up to 1 exactly. So remember,
Okay.
all we're trying to do here is just verify if it's a probability model. So if it doesn't add up to 1 exactly, then it may be a type of model, but it's not a probability model. And that's all we are exploring in this section is the probability model. So if it didn't fit that, then you would just say it is not a probability model. All right. Any questions before I scroll up? A few more details. An event is impossible if the probability is 0. An event is a certainty if the probability is 1. Once again, if we convert it to percentages, probability being 0 means 0% chance. Probability being 1 means a 100% chance. So that's why it's a certainty. That's why the other one is impossible. The closer a probability is to 1, the more likely the event will occur. Closer the probability is to 0, the less likely the event will occur. I know how far I can go up. If I need to come back down, let me know. An unusual event is the event that has a low probability of occurring. And then in red, that's something we do want to hold on to because it'll pop back up every now and then. Typically, an event with a probability less than 0.05 or 5% is considered unusual. So that's going to be what we use as far as determining or establishing what is unusual. But it's not set in stone. So if you were doing your own research, you were doing your own thing, your own uh, presentations or whatever, if you want to establish what's unusual at 7% or even go lower at 3%, then you can. But the normal, excuse me, Typically, that's what you will be measured at. It's at less than 5%. And once again, that's what we will use in this book. If something is less than 5%, then it is considered unusual. All right. Any questions? All right. So calculating probabilities, looking at the empirical approach. So the probability of our event will be the frequency of the event E over the number of trials of the experiments. All right, so an insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim. Based on these results, what is the probability that a teenager will file a claim in a given year? So I'll give you a chance to write that down. All right, so I'm going to find the probability that a teenager will file a claim in a given year. So we know 24 of them did file a claim, and out of the 24, well, not out of the 24, he has 182, and out of the 24, out of the 182, 24 filed a claim. If I can get it out right, right? So we'll just do 24 over the 182, and that 0.132 is the probability. So now in my math lab, they may present your options as far as choosing the answer in word form instead of, sometimes they'll just ask for the number, and sometimes they'll give you like a sentence to choose from. They'll give you four sentences and you have to choose properly. So what it will look like is what's here in the purple. So if it says something like this, so for every 100 teenage drivers, we expect about 13 of them to file a claim. So where they getting that 13 from is from 100 times this 0.132. And you know that 100 times 0.132 is 13.2. So that's about 13. So if they said anything different than that, then you know that wouldn't be the answer. So you would take the 100, that number that they give, multiply it to the probability, and then this number right here should be that result. So in other words, let's say if they said, so for every 1,000 teenage drivers, we expect about, what that would be is 132, because I put 100. But if you take 1,000, multiply it times 0.132, it will give you 132. So it means this number would have been 132 if they said for every 1,000. Okay, so just throwing it out there. If they give you like four sentences to choose from, make sure the numbers lined up accordingly. You take this number right here, multiply it to your probability, and that would be this number. All right. Any questions? Any questions? All right, can I scroll up? All right, so the classical method, stay consistent. Classical method is taking the number of outcomes, and it's still very similar to what we just did. We call it the empirical approach. Classical method, we take the number of outcomes in your event, place it over the number of outcomes in your sample space. Shorthand notation is right here, N of E over N of S. So the number of outcomes in event E over the number of outcomes in the sample space. All right, so let's look at the example of flipping a coin and landing on tails. So landing tails face up. First thing you always want to find, or the first thing that's easiest to establish, is the sample space. Remember, the sample space is going to be the number of all of your possible outcomes of your experiment. So our sample space here is going to be heads and tails, and that's on the two outcomes. On the two possible outcomes of flipping a coin, heads and tails. And so that's why the number of our sample space is 2. Then you explore how many outcomes are in your event. For this one, we want to know, how many different ways can you land tails? There's only one, right? Tails is the only outcome that we're looking at. So once you've established both of those numbers, place the number of outcomes in your event over the number of outcomes in your sample space. So that's 1 over 2, which is a 50% chance of landing tails. So that one, most of you probably already knew without calculating, right? But that's the foundation of what you would be doing with the classical approach or the classical method. Any questions? All right. So next one, a single die is rolled. What is the probability of landing a number greater than 2? All right. So first thing, once again, we want to establish our sample space. So if you ever rolled dice, whether it be in a board game or whatever the case may be, our die will look like this, single die. Let's see. All right, so somebody threw an answer out there. Let's see if she's correct. So a single die, each one of the faces is just 1 through 6. And we have our little pips. 1 pip is 1, 2 pips 2, and so on. So it's 1 through 6. So that's our sample space, 1 through 6. Also, before I go there, so 1 through 6, that means the number of outcomes that we have is 6. Now, what I do want to make sure is that we don't confuse this 6 and this 6 to always have to be the same thing. So this 6 right here could be 1, 2, 3, 4, 5 triangle, but the number of outcomes I have is 6. All right. So this number 6 will be the same as long as there's 6 outcomes, but that 6 is not 6 because you have a 6 right here. So I just want to make sure we're clear on that. I could have had 6 different shapes, and the number of outcomes that we have, is 6. All right. Any problems with that before we go to our event? All right. So now we want to know the probability of, and I'll say this too. So this 6 right here is our bottom number. The number of our sample space, number of outcomes in our sample space is our bottom number. So now we're going to look at our event. Our event is landing a number greater than 2. So when we look at a number greater than 2 as a part of our sample set, in other words, our options, that would be 3 through 6, 3, 4, 5, 6. Numbers greater than 2 that are on the face of this die. So that's 4 numbers that are greater than 2. All right. So now that we have the number of our outcomes in our sample space and the number of outcomes in our event, we'll take the number of our event, place it over the number of our sample space. That'll be 4 over 6. And then you are expected to reduce if possible. So we could divide them both by 2, leaving us with 2/3 as a chance. Got 2/3, 0.67. Any questions?
Quick question.
Mm-hmm.
Can we say the probability is 66%, or we just stick with the fraction?
Leave it as the fraction.
Okay.
My math lab will confirm what answer they want from you. Most of the time it is fraction though.
Okay. Thank you.
Yeah, no problem. Anybody else before we go to the next one? All right. So here we have a pair of dice. It's rolled. All right. Compute the probability of rolling a 7. Then compute the probability of rolling snake eyes, which is rolling a 2. All right. So just like before, first thing you want to do is establish your sample space, the number of outcomes in your sample space. Even if you don't write down each one of the numbers or each one of the outcomes, you at least need to know the total number of outcomes in your sample space. So what we have here is a pair of dice. We have 2 dice. And the way, I'll leave some of it up there. The way our combinations would look is that, you would have to explore when die 1 hits 1 and die 2 hits 1. Die 1 hits 1, die 2 hits 2, die 1 hits 3, die 1 hits 1, die 2 hits 3, and so on. Then you switch it up for 2 1, 2 2, 2 3, 2 4, then 3 1, 3 2. And of course, you don't want to have to do that. So the way you would actually calculate the number of possible outcomes whenever you have this type of scenario, you ask yourself, how many possible outcomes are there for die 1? How many possible outcomes are there for die 2? Multiply those 2 numbers together, and then that will be a total possible number of outcomes. So if I had one die that had 6 faces and the other die had 8 faces, then it would be 6 times 8. So that's how you can do that. That's a short way of establishing the total number of possible outcomes. All right, any questions on that? So we're looking at 36 for this problem. All right, everybody okay with the sample space? All right, next, our event is rolling a 7. So we're going to look at all of the possible ways that we can roll a 7 with these 2 dice. So 1 and 6, they add up to give me 7, 2, 5, 3, 4. Now, die 1 being 3 and die 2 being 4 is a different combination then die 1 being 4 and die 2 being 3. So then we have to explore the opposite of what we've already established. So that would be 4, 3, 5, 2, and 6, 1. All right, so that will give us 6 different ways that we could get, or 6 different ways we could roll a 7. All right, any questions? All right, so now that we have our bottom number, our sample space number, which is 36, and we have our event number, which is 6, and each one of total number of outcomes in our event, total number of outcomes in our sample space, place our event number over our sample space number, which is 6 over 36, and then reduce that to 1 over 6. So we have a 1 out of 6 chance of rolling a 7.
I have a question, Professor. How did you know how to write the the numbers in the order you did, like from 1 to 6 and then the reverse?
Well, you're exploring all possible outcomes, and whenever you do something like this, you do want to be systematic. So now it doesn't matter if I were to say 1 6 and then jump and say 4 3 and then jump and go 2 5. You know what I mean? So that part doesn't necessarily matter. It's just that you want to make sure that you have explored all possible outcomes. So now what you want to do is be systematic. So if I'm going to say 1 plus 6, I know 1 plus 6 will give me 7. So that's why I'm using that. Then I say, okay, 2, is there 2 plus a number that will give me 7? And that is 5. Then I'll look at 3. You know what I mean? So I'll just go down the line. And then once I've exhausted all of my possibilities, then I know I can go on to the next thing. So that's the way I would look at it. You do want to be systematic so you don't leave out, leave out a number or leave out a combination. Hopefully that answered your question.
Yeah, that make a lot of sense. Thank
Okay.
you.
Okay, cool. All right. Everybody good before we go to B? All right. So we're still in the same problem. So we do not have to reestablish our sample space. It's still going to be 36. Still dealing with 2 die. And for future reference, if they give you a pair of dice and there are 6 faces, that's always going to be a sample space. That doesn't change unless you change the number of faces. So as long as each one of your die has 6 faces, 6 times 6 will give you 36, no matter what's going on. All right, so then you ask yourself, how many different ways can you roll a 2? It's only one way. That's when die 1 is 1 and die 2 is 1. So you would take that 1, place it over 36, and that would be your probability.
I'm sorry, Professor. Why would it be 1/36? I'm sorry.
Well, the number of your event. Are you okay with the 36?
Yes.
Mm-hmm.
Yeah, I know that it's 36, but
Mm-hmm.
I was probably asking because of the 1.
Mm-hmm. So it says the probability of rolling snake eyes. So snake eyes is 2. So how many different ways can you get 2 if you were to roll your dice? And there's only one way, and that's when die 1 is 1 and die 2 is 1. I put it 2 is 1. There's no other combination that will give you 2. Like here, rolling a 7, 1 plus 6 gives me 7. 2 plus 5 gives me 7. 3 plus 4 gives me 7. So I have different combinations that will give me 7. There's only one combination that will give me the number 2, and that's 1 plus 1. And so that's only one combination, and that's where that 1 comes from.
Okay, gotcha.
Just like, let's say if they ask us how many different ways could you roll a 3, well, that's when die 1 is 1, die 2 is 2, and then when die 2 is 2, die 1 is 2, and then die 2 is 1. Outside of that, those are the only 2 ways you can get 3. So that means our top number would have been 2 in this case. If we wanted to roll a 3, our top number would be 2. All right. All right, any questions before we look at the next one? All right, so let's look at this next problem. Suppose a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl using the empirical method. Compute the probability of 2 boys and 1 girl using the classical method. So we'll look at both ways. I'll give you guys a chance to write that down. All right, so let's look at A. We want to estimate the probability of having 2 boys and 1 girl using the empirical method. So relatively simple, I would think. Remember, all you do is take the number of, well, in this case, the number of families, total number of families, which is 500, and then the number of the characteristic that you are asking about the probability of, and that's having 2 boys and 1 girl. So we found 180 families out of the 500 had 2 boys and 1 girl. So that's what we did right here, 180 over 500, and that gave us 0.36. Once again, always pay attention to my math lab and how they want the answer. You know, if they want it in fractional form, decimal, I converted it to a decimal because in the book, when they gave this example answer, they converted it to a decimal. So, you know, my math lab, you know, may ask you for decimal, may ask you for fraction. They may give it to you in sentence form, like I mentioned before. If they ask about decimal, make sure you round to the according decimal. So if it's 3 decimals, 4 decimals, or whatever, make sure you hold true to it. All right. Now B, compute the probability of having 2 boys and 1 girl using the classical method. So the way we would do this is do a tree. Am I still copying words? Can everybody go and scrolling? Okay. So what I did here was explore. I'll erase this stuff. I'll put it back up. But so I explored your firstborn being a boy. Then after that, you only have 2 options, boy or girl. So that's what happened there. And after that, you have 2 options from the boy, that's boy, girl. Then you have 2 options from the girl, boy, girl. So ultimately, if you're talking about having 3 kids, you have 4 outcomes from your firstborn being a boy. Then do the same thing for if your firstborn is a girl. And from there, you have 2 options, boy, girl. From the boy, you have 2 options, boy, girl. Then from the girl, you have 2 options. So ultimately, we have 4 possible outcomes. I mean, I said 4 possible outcomes from your first child being a girl, but in total, we have 8 possible outcomes. All right, any problems with the tree before we go any further? And so that's what I was writing right here. 8 possible outcomes in total. And that's going to be the number of our sample space. All right. Now our event is 2 boys, 1 girl. So then you want to look at out of your 8 outcomes, how many produce 2 boys, 1 girl. So it doesn't matter. We're not talking about that the boy had to be first or the girl had to be in the middle or anything like that. So how many different outcomes have 2 boys, 1 girl? And we have these right here. We have 3 different scenarios in which 2 boys, 1 girl was produced. And that's what this is right here. The number of our event, 2 boys, 1 girl, 3. Any problems, any questions? All right, we have our 2 numbers. So we do that 3 over 8. That means our probability would be 0.375 according to the classical method. Any questions, any questions? All right, so that's it for 5-1. 2-5-2. All right, let's see. Do we want to get started in 5-2? Let's see what's going on here. Hold on 1 second. All right, so looking at my math lab, I'm going to pause right here, give you guys a chance. Hopefully, some of you can take advantage of this weekend to, get caught up. We have some people that like they're on task, so it's not a individual thing we're talking about as a class. I want to make sure that I give you guys the opportunity. We don't have the opportunity to do nothing at all. Each day. We got chapter 10. I mean, not chapter 10, 10 weeks. So we do have to do something. But let's see. So for test 1, which is chapter 1 and 2, test 1, you may not have that much scratch work, so we can kind of get by without doing any scratch work. Test 1, so you'll be okay with that. But should have a little work going into the other ones. I'm thinking, but yeah, I know a lot of times when you talk about the scratch work, a lot of times that's for my other classes, like pre-calc and stuff like that. But I do leave it in there generally just in case, we do have it. But we got a lot of application stuff going on, so you may not have that much scratch work when it comes to you guys' tests. So I'll have to go and see, but you should be okay. I know you should be okay with chapter 1's test. that first test. All right. So, come on, guys, let's get in there. The summer will be over before you know it. So you don't want to play around with this stuff. Make sure you get in there, get this work done, try to get caught up to the best of your ability. Because next thing we'll be out of chapter 6 and be looking at our third test. And I know we talked about, at least I believe we talked about this class. Your third test will be proctored. So that one, and I'll give a bunch of options. I'll tell you how we're going to do it, when we get closer to it. But that one will be proctored. So you do want to make sure that you're close to being on task, especially when you get to that point. So before we close out today, any questions? Is everybody good? Everybody straight? All right. So when we pick back up next class, I'll open the floor once again to see if anybody have any questions on anything that may have been generated over the weekend. But other than that, we'll get to 5-2 and keep rolling in chapter 5. So you guys have a great weekend. Be safe, and I will see you on Monday.
So I have a quick question.
Thank you.
Yep. Thank you. Have a good one.
So I have a quick question. On my math lab, I can see the test 2. I don't know what the problem is. I was trying to do it yesterday. But...
Okay, let me see what's going on here. Yep, I forgot to post it.
Okay.
It is assigned now. You should be good to go now.
All right. Thank you very much.
Oh, thank you. All right. Anybody else? Thank you. Miss P. Sean. I think she's going now. All right. You guys take care. Have a good one.
Thanks, you too.
Thanks.
Professor Tucker, I have a couple of questions I wanted to ask,
Oh,
but
man.
it's nothing pertaining to the class. Is that okay?
You just caught me. I hit the end. I had to pull my hand back.
Oh, I'm sorry. I just wanted to be sure that I wasn't cutting anybody off, but I had a couple of questions. It was more so my personal progression in the class, and I wanted to ask.
Yeah, not a problem. Let me stop the recording.
Okay.